Hello everyone, I welcome you all to today's lecture. I am sure you must have gone through the last lecture, but we will have a brief recap of the last lecture today before we start the further aspects of oxidation. What we discussed last time was in detail the Corey-Kim oxidation and Swan oxidation and compared with Kornblum type of oxidations. As we discussed, these three types of oxidations have some common intermediates which are conceptually very similar. For example, in the Kornblum oxidation we reacted DMSO with halide or tosylate and not with alcohols, but it gave an intermediate of this type which upon reaction with a base led to the formation of the aldehyde or ketone as the case may be. So, basically we do not react with alcohols, but we react with alcohol derivatives such as bromide or tosylate. Then of course, we took DMSO based oxidations, different kinds of course, and then we saw the similarity in which a DMSO was activated by an electrophile to form a species of this kind which has a sulfonium ion species and a leaving group. This leaving group is formed because oxygen of the DMSO reacts with the electrophile. So, we have to choose appropriate electrophile such that the OE becomes a nice leaving group. Then the alcohol reacts to form this intermediate which is similar to the intermediate of Kornblum type oxidation. So, conceptually these two are similar, which of course leads in a similar fashion to the aldehyde. Finally, we saw that in Corey-Kim oxidation, when dimethyl sulfide is reacted with N-chlorosuccinimide or chlorine, it leads to an intermediate of this kind, which of course as we saw that we can compare it with this type of intermediate. And since we have a leaving group on sulfur similar to what we had here, but here we had from DMSO and here it is from the dimethyl sulfide. Now this reacts with alcohol to form an intermediate of this type which is similar to the Kornblum oxidation type intermediate. So now what we have is the formation of these aldehydes via conceptually similar sulfonium salts or intermediates which are basically conceptually similar to each other. We also saw various kinds of side products that form during Swan type oxidations arising out of what is called as pumera rearrangement. So, I discussed what was the pumera rearrangement, but in context with the oxidations involving DMSO and an electrophilic species, we saw that an intermediate of this type which has a sulfonium ion and a double bond and a leaving group which can act as a nucleophile, and then of course that can react to form this alpha functionalized sulfide which is also basically a pumera intermediate or pumera type of intermediate. Now in the Swan oxidation, as we saw that we get alpha chlorosulfide which is a pumera type of intermediate. Either this directly reacts with alcohol to form this as a byproduct, or the alcohol can directly react with this sulfonium ion species arising before this chloro species is formed, and then this alcohol reaction with this sulfonium ion species can lead to this byproduct. In either case, pumera type of intermediate is first formed, which is this kind of intermediate or this kind of species. Then we also saw that if we take an indole based molecule like this and react with an electrophile through the pumera intermediate, when the reaction proceeds, it allows the carbon-carbon bond formation to take place here to form this particular final product. Now today we look at another example where the pumera rearrangement has been carried out and the pumera intermediate trapped in intramolecular fashion. For example, if we take a case like this which is similar to this, but somewhat more complicated, having a spiro system here. So as you can see here that we have a part here which can be activated with an electrophile leading to the formation of the pumera intermediate of this kind, as we discussed last time. And then this undergoes cyclization on this particular position, because this oxygen can give electron density and activate the para position, which leads to the formation of the carbon-carbon bond here and eventually to this particular product. So this is another application of the pumera type of intermediates to be trapped in an intramolecular fashion to lead to useful products. Now further utility of the pumera intermediate has also been reported in the literature. If we start with a molecule like this, which of course one can take as a optically active molecule, but now it has a sulfoxide. Now this sulfoxide, when it is treated with trifluoroacetic anhydride in the presence of a base like 2,4,6-colidine, then what is obtained is eventually this particular aldehyde. Now this aldehyde has come from this particular part here, that is CH2SO paratoluene, that means this sulfoxide part, sulfoxide and methyl part here. So now what happens is when trifluoroacetic anhydride reacts with the sulfoxide, the pumera intermediate is formed, which is of this type. Now as we have seen in earlier cases that the nucleophile attacks onto this carbon. Now if it so happens that nucleophile is water, then of course we get an intermediate of this type, which is not a stable intermediate. As you can see, it is basically a hemithioacetal. So this hemithioacetal then undergoes a cleavage and leads to the formation of the corresponding aldehyde. So basically it is a very easy conversion, that if one takes the corresponding sulphide here and oxidizes to the corresponding sulfoxide, then you can straight away go to the formation of the corresponding aldehyde. So this is an interesting utility of the pumera intermediate trapping. Now there is also something called as a Salinofumilar rearrangement. Just the way as sulphides can be converted to sulfoxides and pumera rearrangement can be carried out if we have one hydrogen alpha to it. Similarly, if we take a selenoxide of this kind and if we treat with acetic anhydride, then we can have an alpha acetoxyselenide, because selenides are also important intermediates. Now what happens is that if we somehow get this particular alpha acetoxyselenide, then if we allow the oxidation of selenide to selenoxide to take place, say in the presence of 30% hydrogen peroxide, then it can allow an elimination of this kind involving a 5-member transition state to form the double bond like this, and this is of course a very important intermediate for a number of reasons. Now how does the reaction occur? Of course in a similar fashion as we discussed earlier for sulfoxide based pumera rearrangement, that selenium oxide reacts with acetic anhydride to form the oxygen carbon bond, which then undergoes elimination to form this particular ionic intermediate, to which the acetate ion attacks onto the carbon to form this alpha acetoxyselenide, very similar to what we discussed for sulfoxide based rearrangement. Now if we take an example of this kind, then we see that if we oxidize this selenide to selenium oxide followed by reaction with acetic anhydride, then similar to this we can get alpha acetoxyselenide, which upon reaction with hydrogen peroxide in the presence of pyridine basically to takes care of the acid, then what we see is an elimination towards this side leading to this particular product, and this product can be very useful for a number of different synthetic operations. Now we have to look at it, how does this reaction occur? Of course as we saw that metachlorperbenzoic acid will first convert the selenide to selenium oxide, and when selenium oxide reacts with acetic anhydride, then of course we will get this Salinofumilar intermediate, which upon reaction with the nucleophile present in the reaction medium, that is acetate ion, would lead to acetoxyselenide. Of course this acetoxyselenide then upon oxidation with hydrogen peroxide lead to the formation of the selenium oxide. Now this selenium oxide, as we discussed, leads to this particular product with an elimination on the left hand side. Now if we look at this particular compound here, we can write the structure in this particular fashion, where we have shown clearly the 2 hydrogens on the left hand side. Now this selenide here has alpha configuration, and when the pumera rearrangement takes place and if it proceeds via this selenofumilar intermediate, then obviously we have lost the stereochemistry here. So this acetate can either attack from alpha side or beta side. That means it can be a mixture of alpha or beta selenide. That means this carbon selenium bond can be either alpha or beta. So now if we make the selenium oxide, and for this elimination to occur, we need a 5-member transition state where oxygen takes up the proton from here, and then of course this carbon selenium bond gets cleaved. So whether this is alpha or beta, for both the compounds we have the 2 hydrogens which are available here, because such a 5-membered transition state requires the atoms to be in the same plane. That means if this carbon selenium bond is alpha, then it is much easier for this transition state to form in which this also is alpha. That means alpha hydrogen is abstracted when this carbon selenium bond is also alpha oriented. And of course when it is beta oriented, then this particular proton will be eliminated, but in both the cases we will get the same product. That means elimination on the left hand side is more facile, because there are 2 different types of hydrogens available, and therefore irrespective of the carbon selenium bond stereochemistry, elimination will give the same product. On the other hand, we consider why the elimination did not take place on the right side. Now if the right side, now as we see here that carbon hydrogen bond is alpha oriented. So if carbon selenium bond is alpha oriented, then of course elimination should give this product, but generally we do not see any such product form here or in many cases. And the reason for that is that when this oxygen is approaching the hydrogen which is now attached to the same carbon as OSIR3. Basically what is happening is the electrons on the oxygen are coming very close to the oxygen electrons here, and of course there also will be steric repulsion. So these electronic as well as steric factors do not permit or do not easily allow the elimination to occur on the right side, and thus this product is not formed, and what we get generally is this product. Now there is an interesting reaction on the usage of this sulfur based reagents for the conversion of epoxide to alpha haloketones, and it is published in 1979. It is a very interesting reaction, so I thought that it would be worth discussing it here. So how it is happening is that you take the epoxide and directly convert to the corresponding alpha bromoketone in one step using this reagent. So basically this reagent which is used here is nothing but a combination of dimethyl sulfide and bromine, and this forms a yellow, orangish yellow kind of solid of this type. Of course we can also take dimethyl sulfide and react with chlorine instead of bromine, then of course we will get the corresponding chlorides. That of course is not as stable as this. However, whether we take chlorine or bromine, if we have a species like this and if we react with epoxide, we get the corresponding alpha haloketone. So basically it is a reaction or conversion of epoxides to alpha haloketones in one step employing Swern type oxidation. So I will discuss that how it is Swern type oxidation. Now when this epoxide comes in contact with this sulfonium bromide, then you have oxygen sulfur bond, and then of course you will generate a positive charge on the oxygen. So the nucleophile Br minus opens the epoxide to form an intermediate of this kind, because now Br will be gone as a Br ion, and of course we will get carbon bromine bond here and this intermediate. Now this particular part of the intermediate is similar to Swern type of intermediate, that is the intermediate formed in Swern type oxidation, and therefore if we use triethylamine in the reaction, then of course it will pick up a proton from the methyl, and then the anion will pick up a proton next to the oxygen, and oxidation as we have discussed would take place in an intramolecular fashion to form this alpha bromoketone. As you can imagine that if we take corresponding bromohydrine and then if we react with the Swern type of oxidation or DMSO based oxidation, where DMSO is activated with the electrophile to form this intermediate, and then of course basically doing the oxidation only of alcohol to ketone. But this is already having a bromine. What we are starting here is a different reaction. We are starting with an epoxide and converting in one step to the corresponding alpha bromoketone. Of course if we start with an unsymmetrical epoxide of this kind, then it is difficult to predict where the nucleophile will attack after the oxygen has been activated by sulfur. It could be on this or on this position. Depending on that, we will get a mixture of products. So this is one of the problems or one of the things that one has to consider when we utilize this particular oxidation to form alpha haloketones from epoxide. Now there is another interesting reaction with DMSO BF3 etherate with epoxide. So if we take an epoxide and react with DMSO in the presence of BF3 etherate at 60 degrees, we get the corresponding alpha hydroxyketone. This also has somewhat similar type of oxidation as Swern type of oxidation, but slightly differently. So, we can imagine that DMSO reacts with the epoxide. After the epoxide has been activated by BF3 etherate, the DMSO would open the epoxide in this fashion, leading to the formation of this ionic intermediate, which can be written up like this, where BF3 then comes off. Now, we can think that we have the intramolecular proton abstraction by this way to form the anion at the carbon. Basically this and this is similar, where we have expanded the methyl group to show that the O minus will pick up the hydrogen from here. It can also happen that this hydrogen is picked up by another such species in an intermolecular fashion, essentially leading to formation of this anion, and then this anion will undergo intramolecular proton abstraction similar to the Swern type of oxidation, and then eventually lead to the formation of the alpha hydroxy ketone. So, this is an interesting reaction, which is of course a very unique type of reaction and has been reported in the literature, and which is somewhat similar to the DMSO based oxidations involving the similar type of intermediates as shown here. Now, there is another interesting reaction which is also involving oxidative type of interesting transformations, and it is also by using sulfur based chemistry and similar type of sulfonium intermediates. This involves oxidative decarboxylation of carboxylic acids to carbonyl compounds. That means basically we are starting with this carboxylic acid and eventually converting into the corresponding ketone. What is required is, and this is reported by B.M. Trost several years ago, is we start with the carboxylic acid and react with a base like LDA, lithium diisopropylamide, or butyl lithium, and a disulfide like dimethyl disulfide. Then what happens is, of course, we get alpha functionalized carboxylic acid, which then reacts with N-chlorosuccinimide to form this. How does this reaction occur? The reaction with base yields this dianion, because this will be picked up first and also this will be picked up. Now, this anion or this dianion then reacts with dimethyl disulfide to form this carbon sulfur bond here, because this is more stable than this, and therefore this is less reactive than this anion, therefore this carbon sulfur bond forms. Now, this activation of this particular species with N-chlorosuccinimide in methanol of water forms this particular intermediate, because now sulfur will react with N-chlorosuccinimide to form this sulfonium ion species, which then now, as you can see here, is a leaving group. In earlier cases we had seen that the alcohol reacts onto the sulfur directly, but now here there is no nucleophile present, and therefore decarboxylation occurs, cleaving this carbon-carbon bond and followed by expulsion of the chloride ion to generate this intermediate. If this intermediate is formed, then of course water can react during the workup, and what we can get is this hemithioacetal, which then cleaves and leads to the formation of the corresponding ketone. So, this is how a very interesting oxidative decarboxylation of carboxylic acids to carbonyl compound has been reported by Trost. Now, we discussed the eliminations of selenium oxide, but we also will now look at the elimination of sulfoxides little more carefully and with the mechanism. Sulfoxides or selenium oxides with a beta hydrogen undergo syn elimination on heating to form alkenes. Now, if we take the sulfoxide here with this particular stereochemical dispositions, then we can see that there is an alpha hydrogen, there is also a beta hydrogen. So, if we heat at 80 degrees in benzene or toluene, we get this particular product as the final product formed in this reaction. Now, what happens is that if we write it in this particular fashion here, like what we have done now here is basically put it in such a fashion, everything is same, so that this carbon hydrogen which is here is beta oriented, this carbon sulfur bond is also beta oriented. That is exactly what we have written it here too, except that it is slightly differently put. But now this hydrogen, this carbon, sulfur and oxygen, they are all in one plane, and then syn elimination takes place because carbon, hydrogen and carbon sulfur bonds are in the same direction. This syn elimination leads to the formation of this pair of olefin. Now, it is a stereo selective elimination. So, that means if we take a sulfoxide of this kind where there is a hydrogen and also deuterium, if we write the conformation, so the carbon sulfur bond is beta oriented and then the hydrogen which is beta oriented is axial and deuterium which is alpha oriented is equatorial, and of course tertiary butyl which is beta oriented is also equatorial. Now, for this elimination to occur, obviously carbon, sulfur, oxygen and this hydrogen, carbon etc., they are syn disposed. So, now this syn disposed species then undergo syn elimination to form this particular olefin. So, this is the example of elimination of sulfoxides to olefin. So, in a similar fashion selenium oxides also undergo elimination. Now, one of the products that has been utilized is in this particular type of transformation is that we start with this ketoester, then we can get the corresponding sulfide here by first protecting this ketone as a ketal, followed by LDA deprotonation here and then reaction with dimethyl disulfide. Then we can remove this ketal from here and then that leads to the formation of this intermediate. That means this particular intermediate is formed after the third step, and the fourth step, that is the hydrolysis of this ketal, leads to the release of the ketone here. So, that will lead to the formation of this particular thio intermediate. Now, if you make the sulfoxide by using sodium metaperiodate and heat it, then of course via the sulfoxide elimination occurs and of course we get this particular product as the final product, which is basically a pheromone which I discussed earlier in the first lecture, that this is a pheromone of queen honey bees. Now, we can also carry out another interesting reaction where now we are going to use similar type of selenium oxide based elimination, and that is if we take an alpha beta unsaturated ketone of this kind and react with lithium diphenyl cuprate and react with phenyl selenium bromide, then we get this type of selenium intermediate which upon reaction with hydrogen peroxide leads to the formation of the double bond. What happens is of course lithium dimethyl cuprate will add in a Michael fashion here, and the corresponding enol cuprate then acts as a nucleophile to react with the electrophile, that is phenyl SEPR in this fashion to form this trans intermediate. That means this carbon selenium bond will be opposite to the carbon phenyl bond, and if this happens to be a beta bond, then of course this will be an alpha bond. Now this carbon selenium bond which is alpha oriented and the carbon hydrogen bond which is here is also alpha oriented as shown here, then when hydrogen peroxide is reacted with it, it forms this selenoxide, and this selenoxide has a carbon hydrogen bond which is in the same stereochemical disposition as this carbon selenium bond, and this undergoes syn elimination to form this enone. So this is how even selenoxide based syn eliminations have been utilized. So we will stop it here today and take up some other aspects of this kind of chemistry next time. Till then, bye.